So now we are looking for you are asked to draw the bending moment diagram and the shearing force diagram for a simply supported beam whereby whereby we have a uniformly distributed load on the full span. So now before we draw according as I've been saying earlier on simply supported beam, before we draw the shearing force diagram and the bending moment diagram or do any calculations at all, first of all, we have to find for the reaction at B and the reaction at A. So now let's say the reaction at B. So we have the reaction at B times the length, that is the full length, will be equals to what is our bending moment here? We have W times L square over 2. So if we divide this thing by L, we divide by L, we have R of B to be equals to WL square all over 2L. And one L will cancel this here, so it will be equals to WL over 2 kilonewton. So that is our reaction at B. But our reaction at A now is equals to we have our reaction at A is the total shearing force minus the reaction at B. We have the total shearing force here, which is WL minus our reaction at B, which is WL over 2. If we collect like terms here, we have 2 here. We have 2WL minus WL, which will eventually give us WL over 2 kilonewton. So that is our reaction at A and our reaction at B. So now looking for the shearing force at B, our shearing force at B would be the same reaction at B because we do not have another load on top that particular point or after the particular point. So we have our shearing force at B to be equals to reaction at B, which is WL over 2. WL over 2. So that is our shearing force at B kilonewton. Now our shearing force at point X here. Our shearing force at point X here would be equals to this reaction B, which is WL over 2, which is positive because it is pointing upward. Then minus the shearing force, that is this uniformly distributed load. What is the shearing force? That is the load times the distance, which is W times X, which is WX. That is our shearing force at point X here. Then our shearing force at point A would be equals to we have WL over 2 minus what is our distance here? WL, which will still give us WL. So it will be something like negative WL over 2. Since shear force at B, if shear force at B is positive, then shear force at A will be negative. So that is for shearing force. Now for the bending moment calculation, we have the bending moment at B will be equals to 0 kilonewton meter. That is the bending moment at B. Now the bending moment at X now will be equals to this reaction B, the reaction B here, we have RB times X, which is here. Now minus, because in this place we are dealing with a load that is coming from upward. So we have our shearing force at here, our shearing force at X. We have our shearing force here, which is WX times the distance from the moment of inertia from here to here, that is from half point here, it will be equals to times times X over 2. So our reaction B here, which is WL over 2, it will be equals to WL over 2x minus WX squared over 2. So this is our bending moment at X. So now in a U.D.L, we need to consider the highest moment, that is the highest moment of the highest bending moment, that is the distance, the highest moment to be. Because in a bending moment, the diagram is going to be in a curve form. So we need to find for this peak value here, that is this peak value that is at this point here, which is the max bending moment. But the peak value, which is the max bending moment, only occurs where the shearing force is equal to zero. So if our shearing force, if the shearing force of x is equal to zero, that is using this, if the shearing force of x is equal to zero, what is x? So right here, we have our shear force of x equals to zero. We have WL over 2 minus WX is equals to zero. And we are looking for x. So we have, bring this here, we have 2, we have WL minus 2WX is equals to zero. If we cross multiply, we have it as WL minus 2WX is equals to zero, because 2 times zero is zero. So we can still bring out W as subject of the formula here. W open brackets L minus 2x equals to zero. Divide both sides by W. W cancel zero. W cancel W. Zero divided by W is zero. So we have L minus 2x is equals to zero. We have minus 2x is equals to minus L. Divide both sides by minus 2. Minus 2 cancel minus 2, minus cancel minus. We have x is equals to L over 2. So the distance where the shearing force is equals to zero is when the distance of the span, the length of the span, is at the half point, exactly half point. So the bending moments at the max where x is equals to L over 2, that is when we went at max, it will be, that is this, wherever we see x, we are putting L over 2. So the bending moment at the max will be equals to W L over 2. What is our x? L over 2. That is, this is minus W, we put over 2 here. Our x here is what? L over 2 then square, because we have x square right here. So L over 2 square. So here it will be equals to WL square over 2 times 2, 4, minus we have W over 2 times this, which is L square over 4. It will eventually become WL square over 2 over 4 minus WL square over 8, which is 2 times 4, which is our 8. So we find for the LCM, which is 8. Since the LCM is 8, we have, it will be 2WL square minus WL square, which will be equal to WL square over 8. That will be our max bending moment. Max bending moment will be equal to WL over WL square over 8 kilonewton meter. That is what it will be. Then our bending moment at A here would also be equal to 0. The bending moment at A will be equal to 0 kilonewton meter. So that is it. So drawing the diagrams for this, we put a neutral line of 0. Then at B, the shearing force at B, WL over 2, the shearing force at X is this. So let's say we trace, we draw our diagram here. This X is right here. So now we have here to be WL over 2, here is WL over 2, and we have, it will hit the midway point to reach here. And this point here is where we have L over 2 from here. So from here, this is where L over 2 is. So here we have WL over 2, we have WL over 2. Here would be WL over 2 minus WX, that is the shearing force at X, and here is 0, is 0 point. So that is for, we have this as our negative, and here is the positive. So this is our shearing force diagram. Then for our bending moment diagram, our bending moment at B is 0, bending moment at A is 0, then the diagram would look something like this. It looks something like this. That is to be in a curved form, to be curved. So this point here is here, which is WLX over 2 minus WX squared over 2. And here will be WL squared over 8. That is the distance from here to here. So this will be our bending moments diagram. That is our bending moment diagram and our shear force diagram for a uniformly distributed load on a simply supported beam.